Hello everybody, this is Dr. Christopher White and welcome back to the second half of the exercise 16 video. So we've actually skipped part C and we've moved on to part D, so you will not be doing part C. I repeat, you are not doing part C. So part D is dealing with the Black Hills and High Plains of South Dakota. So one of the reasons that I've selected this particular exercise is that the geologic map associated with it is kind of more realistic of what geologists have to deal with on a regular basis. So you can see this is a pretty complex map. Now compare that to some of the maps we've been dealing with. You know, you can quite clearly see the beds of rock, everything looks quite nice, and then you compare it to that, well, it's quite a different world, isn't it? So what can we see? Well, your eyes are instantly going to be drawn to one feature, aren't they? You can quite clearly see we have this feature right here in the middle. Okay? And then over here on the right, you can see we have the plains. Okay? So we're going to investigate these two areas. Now once again, we have ourselves a 2-page key. So we have some Precambrian rocks here. Now we have 3 igneous rocks here. Now they are undated, so we don't know where they sit in the sequence. So they are just simply put by themselves. In terms of the Precambrian rocks, you will notice that we have a lowercase p followed by an uppercase C with a line through it. So obviously the C with the horizontal line through it, that's the symbol for the Cambrian. And the little p in front tells us it's Precambrian. Then of course as we drop down here, we have the Cambrian rocks, C with a line, Ordovician, O, Mississippian, C, Pennsylvanian, C, because obviously both Carboniferous, Permian, P, Triassic, TR, Jurassic, J, Cretaceous, K, Tertiary, off the top of the shot there, T. Okay, so what you'll notice is that for the Cambrian, Ordovician, Mississippian, Pennsylvanian, Permian, Triassic, and Jurassic, we're pretty rock light, aren't we? Now obviously, you know, not much was really happening at those points, and of course if we look up here, the Cretaceous was clearly a period of a lot of action by comparison. Okay, so let's have a look at the questions. So look at the geologic map. Done that. What are the ages of the rocks shown on the map? Well, that one's actually quite straightforward because we can just lift the ages from these 2 pages here, can't we? Okay. Now, don't give me the range. Actually, give me the individual periods, because some periods are, of course, missing. So, just take note of that, please. Obviously, ignore the igneous rocks because they are undated, and as such, we don't have that information. Okay, so that's question 1, easily done. Question 2. What type of geologic structure is represented by the belted elliptical outcrops? Alright, so right here, this brown area is our belted elliptical outcrop. Let's analyse it. Okay, so in the middle here we have a mixture of brown rocks. All of them have lowercase p's in front of C's with horizontal lines through them. So what we have here are a load of Precambrian rocks. And what we have around the margin of the Precambrian rocks is essentially a bed of kind of orange-brown rock. Okay, well, orange-brown, color on the map rock. Now this is the Cambrian. So this Cambrian follows all the way around the margin of these Precambrian rocks here. So the Cambrian rocks are essentially, belting, for want of a better way of describing it, the Precambrian rocks. They are fully surrounding it. Okay. So then what we're going to do is we're then going to try and step out, and we're going to see what kind of rock, what other rocks we have. Okay. So our next rock we'll be keeping an eye out for is OW, the purple rock, which is going to be Ordovician. So now, as you can see, this is a very complicated situation. So, this one's going to be rather tricky. I can't see any OW in this area, so this would rather suggest that if it's going to... there we go, OW. Okay, so OW is lurking in this upper region here, But as we can quite clearly see, this upper region here is, shall we say, complex. So it's a little bit difficult to actually see exactly where OW is. So I may have to, admit defeat on that one. When it comes to coming down and around here, I've got to be honest, I can't see any OW whatsoever. No, can't see it. Nope, not happening. Okay. So next is going to be CP and CM. CP is essentially a limestone, and CM is a sandstone. They're both Pennsylvanian in age. Why that one's CP and that one's CM is a little bit confusing to me. I do wonder whether it's a typo maybe. But anyway, CM is the Pennsylvanian, CP is the Mississippian, sorry. So let's see if we can find them. Okay, here we go. There's CP and there's CM. Okay, so remember CP is the Mississippian, so that's the older one, and CM is the Pennsylvanian. So far we've gone Cambrian, Mississippian, Pennsylvanian. So as you can see, we're stepping out slowly. Okay, and as you can see, the age is getting lower so far. Okay, so let's keep going with that. So next we're looking for the Permian, which is going to be a solid blue. Now that one's an easy one to find because you can't really miss it. It's right here. Okay, very, very clear, very, very easy to see. Okay, so good, we've taken care of that one. Next is going to be the Triassic, which is going to be a blue-green diagonal. So can't really miss that either, it's right here. Okay, so the Triassic, that one is easily spotted, good. That's going to be then followed by the Jurassic, so JS and JM. Well, JS is very easy to spot, it's right here, and it comes all the way around. Now JM, where is JM? Oh, here's JM, right here. So JM is this darker line right here. It's a very, very thin bed. You can't really see the bed itself at all, actually. It just looks like a very thick line. Now then we have all the Cretaceous rocks. So if we look at the Cretaceous rocks, most of them are forming a band, which is coming up around here, coming down. Now it narrows a bit here, but then it balloons out again down here, and then comes round like so. So what you can see is we have several different beds of rock that are essentially surrounding this core. Okay, or for want of a better term, belting it. Okay, so the last rock in the Cretaceous, however, KP, is actually out here on the plains. It's not part of this feature. On top of KP, we then have TW, which is the tertiary rocks, and you can see that TW are forming these kind of linear features. And this is a classic indicator that TW is probably related to river processes. Okay, so now we have to think about, well, what could this feature be? Now, unfortunately, we don't have any dip symbols. A dip symbol right now would be spectacularly helpful, but the map doesn't have any. So we're going to have to try and work this out for ourselves. So what we do know is that in the center of this feature, we have the oldest rocks, and the rocks are steadily getting younger as you head towards the margin. Okay. Another thing we can see about this feature is that it's elongate, and it's narrowing towards its bottom, and it's narrowing towards its top. Okay, so it's not a circular feature. If it was a nice circular feature, obviously it would be something like a basin. So I'm just gonna excuse me for just 1 second. So I'm just gonna go to this computer screen for just a moment. So if we come over here, you can quite clearly see that the circular feature, which is the Michigan Basin. Okay, and you can see it's excuse me, you can see it is pretty equal in all directions. Okay, now what the feature we have here is not. It's more lenticular, it's more eye-shaped. Okay. Okay, so Oldest rocks in the middle, youngest rocks on the outside, lenticular, elongate shape. Okay, so there's only, it's a fold of some kind, and there's only really two options when it comes to these kind of larger folds, or smaller folds, I can't think of it, and those are anticlines and synclines. So you're going to have to work out whether this is an anticline or a syncline. So if you remember, an anticline forms an arch. Okay, well, it should have done this, forms an arch, whereas a syncline will form a trough. Okay. Now, in terms of what's going on over here, you would assume the rocks are horizontally bedded, or relatively evenly, or relatively horizontally bedded, as opposed to this stuff over here, which is obviously going to be dipping, because obviously if it's an anticline, it's going to be coming in like this, so it's going to have some dip. If it's a syncline, it's going to be coming in like that. So all these beds here are going to be dipping in some way, depending on what kind of feature it is. This stuff out here probably is going to be, it might be dipping, but probably not at such a steep angle. Or it could be perfectly horizontal. We just don't know, because there are no dip symbols on this map, which is a travesty. Okay. So you're going to try and work out what the type of geologic structure is. Okay. Question 3. What kind of rocks are exposed at the core of the Black Hills, along the flank and in the plains to the east? Well, we've pretty much covered this, haven't we? So we know we've got the Precambrian rocks in the core. We have a mixture of Paleozoic and Mesozoic rocks essentially surrounding it, forming a concentric circle around it. And then obviously out here we have KP, which is the youngest of the Mesozoic rocks, and then obviously on top of that we then have this tertiary cover. So answer that as you wish. So take information from the map obviously, but also take information from the key as well for a nice complete answer. So question 5. Locate and describe a nonconformity, disconformity, and two angular unconformities. Okay, well, a nonconformity should be pretty easy to find on the map, because a nonconformity is, of course, where we have sedimentary rocks in contact with either igneous or metamorphic rocks. So just find anywhere on the map where you have sedimentary rocks in contact with either igneous or metamorphic rocks, and you've done it. So what about a disconformity? Well, a disconformity is, of course, where you have horizontally bedded rocks above and below the unconformity, and the unconformity itself undulates. So what we're looking for are beds of rock which are running parallel to each other. The contact between them will be, will wiggle a little bit. But what you need is to know that there is missing rock in between them. So how do we know whether there's missing rock in between them? The answer is you hit the key. Because the key is going to tell you whether you're missing rock. Okay? So for instance, if the Permian isn't listed in the key, well, clearly the Permian isn't in the sequence, so it's been eroded away, so you have an unconformity there, don't you? So just bear that in mind. I'm sure you can also crack that one quite easily. As for the angular unconformities, well, that one is also relatively straightforward. If you remember, an angular unconformity is tilted rocks below the unconformity and horizontal rocks above the unconformity. Now, we've already discussed where on this diagram you can find rocks that have dip. Okay, so I'm not going to tell you that, but all you need is an area where you have rocks that have dip coming in contact with rocks which are essentially horizontal. Okay, so I think you can probably crack that one as well. So question 6 is, where is the most likely area in the Black Hills for commercial mineral production and why? Okay, well, a lot of mineral production, a lot of mineral deposits are the result of what we call hydrothermal fluids, so hot water. So what hot water does is, as it moves through rocks, it has a very interesting habit of doing what we call scavenging. So it will steal metals from rocks as it goes. So it will steal all those metals, and then, if conditions are right, somewhere in the sequence of rocks, it will deposit those metals. And if you get enough of those metals being deposited in a relatively confined space, essentially you have a mineral deposit and you can mine it and you can make some money. So what we need to look for is we need to look for something in the area that would be capable of driving fluid circulation. So let's have a look. Okay, so what we're really looking for is we're looking for TP. So that's red, light-coloured intrusive igneous rocks, because they're going to be hot, aren't they? And a hot rock intruded into the crust might be sufficient to drive fluid circulation. And we can't really miss it. Okay, now once again, we're looking for TP. Okay, so TP is going to be a light red colour. And well, I'm sure we'll find it. It'll be mixed up in here somewhere, so keep your eye out for TP, and that will probably be your source for fluid circulation. Okay, so what about part E? Well, we're not going to do part E, because part E is, once again, a question that involves linking together stratigraphic columns, and I've got to be honest, I don't think it's a particularly good question, so we're just going to skip past it. I think it's a lot of work, and it doesn't really get you much reward at the end of it. So now we're going to move on to part F, which is the final part of exercise 16. So in part F, what we're doing is we're going to look at we're going to try and construct, should I say, a Lithofacies map. So Lithofacies maps require geologists to go to locations which are the same age. And at every location they go to, they'll try and they'll work out what the rock is. Okay, now remember, all these rocks have to be the same age. They'll look at what the rock is, and they'll try and work out what the environment of deposition is. And so then what they'll do is they'll take all this information and they'll put it onto a map that looks like this. Okay, so as you can see, we have all of these locations, and for each location, in this case, they have given the rock. So you can see out here we have a whole load of M's. That stands for marl or chalk. So those are essentially deep marine sediments. We have a load of points marked SH. That stands for shale, so muddy sediments. We then have some points marked SS. That stands for sandstone. And then we have a range of points called conglomerate, so CONGL, that stands for conglomerate. And if you remember, conglomerates tend to occur in more higher energy environments, normally associated with elevated terrain, so we're talking hills or maybe even mountains. So okay, so as you can see, we have these four different facies essentially: a conglomerate facies, a sandstone facies, a shale facies, and a marl or chalk facies. So what are we going to do? Well, the first thing we're going to do is we're going to try and use this information to produce a crude map. So how do we do it? Well, if you have the hard copy, it's time to break out the coloured pencils and select 4 colours. And what you're going to do is you're going to assign 1 colour for the marl, 1 colour for the shale, 1 colour for the sandstone, and 1 colour for the conglomerate, and you're going to colour in each of these points. Now, if you're on the computer, you're going to take a screen grab of this, and you're going to do the same thing, but you're just going to drop coloured circles or coloured squares over each of these points. Okay, so you're going to have a map that is covered in essentially 4 colours. And what you'll notice is these locations kind of cluster together. And so what you'll do is you will draw boundaries in between these different lithofacies. So if we look up here in the top right corner, you can see we have a selection of M points right there. And here we have a pile of SH points. So we have a load of shale outcrops here and a load of marl outcrops right here. And so we'll just simply drop our boundary in the middle between the two. So our boundary will just come through here like so, in an equal distance between the points. And so this would be our boundary right there. So it's a relatively straightforward process. So just run the boundary at an equal distance between the 2 points, and you can't really go wrong. So okay, so that's the first part. Relatively straightforward, I hope. So question 2. do the facies belts, or do the facies belts parallel the zero thickness line? So what's the zero thickness line? Okay, here we go. So the line of zero sediment thickness, the dashed line, in the western part of the map represents the position of the Cretaceous shoreline, so the coast. So let's have a look and see what we can find. Okay, here it is. So here is the coastline, the line of zero thickness. So, okay, what do we see? Well, we see this line of zero thickness has a general north-south trend to it. Okay, it wiggles around a bit, but on the whole, it's north-south. So once you've drawn your lithofacies, regions, if they're orientated in kind of a crude north-south orientation, then yes, they run parallel to the coastline. If they, on the other hand, do not, well, clearly, they are not parallel to the zero sediment line, are they? All right, so once I can't really help you with that too much. You'll work it out once you've drawn your boundaries in and once you've defined your zones. So on to question 3. So what was the direction of transport of the sediments? What was the probable source area for the coarse sediments along the western border of the map? Okay, so over here we have several points of conglomerate, don't we? And we know that conglomerate is associated with areas of elevated terrain. So we can probably say that we have an area of elevated terrain running along here. I wouldn't say that's too much of a, too risky a guess. So that of course means, well, where's the sediment coming from? Well, the sediment's coming from the elevated terrain. Rocks in the high areas are being eroded and they're forming sediment which is being transported and depositing into our ocean basin here, or sea basin. Okay, now this means that we have high ground over here, and that means our sediment is going to be going that way, doesn't it? It's going to come off the high ground and flow into our basin. Okay, so once again, I don't think that's too much of a jump to make. Okay, now we also know that the sediment transport would be in that direction because we know we have deep water over here and we know we have shallower water over here. In fact, we know we have our coast right here. So we know the sandstones here would be shallow marine, the shales here would become like moderate marine, and then the marls would obviously be deep marine. So once again, we know the sediment must be going this way because we're going from shallow marine to moderate marine to deep marine. Question 4. Were the Colorado Rocky Mountains present during the deposition of these sedimentary rocks? And so what's your evidence? Well, were the Rocky Mountains there? Well, the answer is probably yes. There's definitely some kind of elevated terrain here, isn't there? Which is allowing the conglomerate to be produced. So something's going on. It's difficult to definitively say though, isn't it? Okay, so we have evidence that would strongly suggest the evidence or the possibility of the Rockies being there, but based on what we've got here on the map, it is difficult to conclusively prove. All right, so the conglomerates suggest yes, but conglomerates by themselves maybe aren't really enough to make a definitive case, are they? So, chances are we're probably right by saying yes, but at the same time we can't be certain. Okay. And then finally we have question number 5. Question number 5 is, where would you expect the greatest thickness of sediments to have accumulated and why? Okay, well, for this we actually need to go back several pages. So what we need to do is we need to come all the way back to page, give me 1 second, we'll find it, to page 242. And here we have the Sevier Foreland Basin. Okay, so over here we have the elevated terrain, the high ground of the Sevier Orogeny. And this high ground was being eroded and it was depositing sediments into a small basin to the east. Now the sediments closest to the mountains are quite coarse. So it's going to be a selection of alluvial sediments and, conglomerates. So we're going to have lots of very coarse sediment right next to our elevated terrain. Now, as you move away from that, the size of the sediment is going to get smaller. So we're going from a conglomerate over here, into a sand here, and into a mud here. Okay? Now, the thing we have to remember is this. When sediment is entering our basin, the vast majority of it gets dumped pretty much right here. So that means most of the sediment is going to get dropped right there. And this means over time, the amount of sediment in this area is going to get higher and higher and higher. It's going to get heavier and heavier and heavier. And of course, as we discussed earlier, it's going to start down warping the crust right there, isn't it? The sheer weight of the sediment's going to start pushing the crust down. And obviously, as the crust drops down, it creates an even deeper depression, which means more sediment gathers faster, and so on and so on and so on. And essentially, it's a vicious cycle. The more sediment you dump, the more this drops, leaving more room for more sediment. So where would we find the greatest thickness? Well, we would find the greatest thickness pretty much right next to the high ground. So if we go back to our diagram, where do we find our high ground? Well, remember, we're assuming the presence of high ground based on the conglomerate, so we're assuming our high ground is probably coming down here along the coast, which means this area right here, where we have our conglomerates and sandstones, that's probably where we would expect the greatest thickness of sediment to be building up. You can never be certain, but that would seem a relatively safe assumption to make. Okay everyone, so that's the end of exercise 16. I think we've gone through it relatively thoroughly, so I think everything should be okay. So once again, everyone, take care.